Now in our toolbox, we need to deal with a very important issue. How do we deal with sample design and power calculations? In this module, our goals are to familiarize you with the basic issues that underlie sample size calculations, to walk through the steps of real calculations using an example, and point out some additional wrinkles that you might encounter. One of the big issues is how big a sample size do we need? In planning this stage of the study, a key activity for the researcher is to determine how many participants they need to enroll in the study, how many observations we need. A study needs to be large enough to distinguish the true difference from random variation. Let's look at this hypothetical example. Below, we have two graphs, one where the sample size is 100, the one on the left, and another where the sample size is 1,000, the one on the right. There are two distributions, the treatment group and the control group, the blue and the black group. In both of them, the mean of the blue group is 60 and the mean of the black group is 50. The difference between those two means in both cases is 10. How do we know whether or not this difference of 10 is statistically significant? Well, what we're going to do is we're going to look to see whether or not the distributions are separate. On the left, the black and the blue distributions overlap, so we really don't know whether that 10 is really statistically significant or not. On the right, the blue distribution seems to be separate and further to the right than the black distribution. In this case, it looks like the difference is real. Well, what's the big difference between the distribution on the left side and the distribution on the right side? Well, the distribution on the right side has 10 times the number of observations as on the left. In general, the more observations we get, the more the distribution collapses around the mean, and the easier it's going to be to distinguish differences in means. However, we don't want a very, very large sample size because that would be a waste of time and resources and has ethical implications. We don't want to impose undue burden on the study population, and at some point, study logistics begin to threaten internal validity. When designing a study, we're typically interested in one of two related questions. First, given a desired minimum detectable effect, how large a sample do we need to do the study? Second, given a fixed sample size and design, what is the minimum detectable effect that the study can detect? Tied up in both of these questions is a decision of how much power we want the design to have. Let's take an example. Does swimming in marine water increase the risk of gastrointestinal illness, or GI? Here's the general setup using the water example. Our research question is, does swimming in the marine water increase the risk of GI? Swimmers, A equals 1, and non-swimmers, A equals 0, are enrolled at the beach and followed for 2 weeks for incident GI. That will be the dependent variable Y. Our parameter of interest is the risk difference between the two groups. So in this case, it equals to the difference in the probability that the group of swimmers has a GI minus the difference in the probability that the non-swimmers had GI. That difference is what we're interested in estimating. The question then is, how large does the sample size need to be to credibly detect a 1 percentage point increase in the cumulative risk from a base of 3.4%? This is the equivalent risk ratio of 1.3. The idea here is that at baseline, or in the control group, we have a 3.4 percentage percent incidence of GI. How much sample size do we need to observe that going from 3.4 to 4.4? There are 3 technical details that we need to consider. It's common to use statistical power to help determine the size of the study. Statistical power is defined as the probability of rejecting the null hypothesis when it is false. Implicit in this definition is that an investigator must specify a null and an alternative hypothesis. The power is defined within these specific hypothesis tests. From the recreational water example, the null hypothesis is there is no effect. Water does not increase risk. The alternative hypothesis is there is an effect. Water exposure increases risk. You can think of these scenarios as true alternatives, but both cannot be true at the same time. Exposure to water can not both have no effect on GI risk and have a positive effect on the risk. So now what we need to do is pick a test statistic. Given a specific hypothesis, we're going to have to figure out how we test this. An example of a commonly used test statistic is a Wald statistic, which is the difference between the two group means divided by its standard error. A Wald statistic will have a standard distribution under the null hypothesis with mean 0 and standard deviation 1. We need to specify critical values based on what are called type 1 and type 2 errors. These issues are illustrated in the matrix below. In the columns, we have which hypothesis is true. The first one is the null hypothesis true, and the second one is the alternative hypothesis true. In the rows, we identify whether we're going to accept the null hypothesis, the first row, or whether we're going to reject the null hypothesis. If the null hypothesis is true and we accept it, that was a correct decision. If the alternative hypothesis was true and we reject the null hypothesis, that's also a correct decision. Those are on the diagonals of the matrix. The non-diagonals is when we find an error. Type 1 error is when the null hypothesis is true, but we reject it. That's a type 1 error and is commonly called alpha. When the alternative hypothesis is true and we accept it, that's called a type 2 error, or beta. We can get some intuition as to type 1 and type 2 errors by looking at the distributions of the variables. Type 1 error is the probability that the area under the null distribution of the variable x to the right of the critical value. If alpha equals 0.05, then the critical value is the 95th percentile of the standard normal distribution. And if you look at the curve below, the critical value z1 minus alpha, the area under the curve to the right of that is the type 1 error. In this case, a 0.05 region, or a 5% probability of a type 1 error that we reject the null hypothesis when it's true. The null and the alternative distributions for x are displayed below. When the null is true, the blue distribution is active, and when the alternative is true, the orange is active. We choose a critical value z1 minus alpha, and that's the dotted line. The type 2 error probability is the area under the alternative distribution to the left of the critical value. Below, that would be the gray area to the left of the critical value dotted line under the orange distribution. 1 minus beta is the area under the alternative distribution to the right of the critical value. That's power. In this graph, the area under the orange curve to the right of the critical value. How can we increase the power for a fixed effect size? That is, we want to test whether the difference in two means is greater than or equal to some effect. We're going to do that by increasing the sample size. When we increase the sample size, that decreases the standard error of the estimate, and you can see that by the distributions becoming taller and skinnier. In the case of the alternative distribution below, the orange distribution, as sample sizes increase, we go from the faded orange line to the solid orange lines, and you can see that distribution become skinnier. For the null distribution, the blue line, you can see the blue distribution, you can see as sample size increases, that we go from the faded blue line to the solid blue line, and the distribution becomes skinnier. What's interesting about this is if you look at the power for a critical value of z, you can see power increases when sample sizes go up as the gray area gets bigger. The other thing we could do is we could change the critical value from, say in this case, an alpha equal to 0.05, or which is z 0.95 to z0.9. In this case, the dotted line, the critical value, moves to the left, and that increases power. You can see that by the difference in the two dotted lines under the orange curve. So now let's go back to our example of recreational water study. Our specific hypothesis is the null, there's no effect. The alternative, there's a positive effect. We pick our critical values, say 80% power, and we'll pick a 5% type 1 error for a one-sided t-test. We specify the parameters required in the calculation. P2 equals 0.034 cumulative incidence among swimmers from a prior study. That's our baseline effect. We pick P1 equals 0.04. This is a 1 percentage point increase off of P2. We calculate the sample size. We can do that by hand or with software. But remember, most hand calculations diabolically strain human limits, even for the easiest formula. We recommend you use software, such as the SampSci command in Stata. Here we show you the output from Stata for the recreational study. What sample size would we need to detect a 1 percentage point difference? Well, here we have the command SampSci 0.0442 space 0.043 with a alpha 0.05 and power 0.8 for a one-sided test. And you see below we need 4,465 observations per arm of the study in order to detect a 1% percentage point difference with power of 0.8 and alpha 0.05. So, in terms of doing power calculations, sample size calculations require that you specify the basic design, the fraction treated, the parameter of interest, and a hypothesis, the outcome variability, that's not for 0, 1, or binomial outcomes, the minimum detectable effect you're interested in, desired level of power, and type 1 error. There are additional complications that we didn't cover in this introduction, which is what if you have a clustered design, number of clusters you would need, number of units, and the intercluster correlation. That will be dealt with at a later date. Finally, these calculations are important, but ultimately they rely on a lot of guesswork. In practice, there's a lot of interplay between the budget, the science, and the sample size. Some people call this the sample size samba.